All right, excellent. So thank you, Kira, thank you, Chava. So it's my pleasure to introduce our speaker for today, who is Dylan Foster. So I suppose many of you know Dylan. He's an absolute superstar when it comes to learning theory and contextual bandits and reinforcement learning. He's been doing some truly amazing work on all of these topics. He's currently a research scientist at Microsoft Research. Before that, he was a postdoc at MIT with Sasha Raklin. And even before that, he did his PhD with Kartik Shritharan at Cornell University. He has many awards, several Best Paper awards from Colt, and overall, yeah, his research has been very influential. He's done some great work on contextual bandits that he already gave a talk about last year at the seminar, and he's giving us some updates, which is apparently a pretty comprehensive theory of statistical complexity in directed decision-making. So with that, I'm going to pass it over to Dylan. Thank you very much for accepting our invitation.
Cool. Thanks a lot, KK. Yeah, so let me just say, yeah, of course, thanks for having me. And before I start, yeah, so I think probably, so I can definitely answer clarification questions and so forth throughout the talk, but I think for the more technical questions, it'll probably be better if we save these for the end, once we have a chance to get through kind of the main results. But yeah, so let me just dive in. Yeah, so this is, as Gary said, it's a talk about interactive or say data-driven decision-making. And, when I say data-driven decision-making, really what I'm talking about is problems where we're interacting with an unknown environment and we're trying to make these decisions like what treatment do we give to a patient or what signal do I send to a robot's actuator. And of course, I'm saying data-driven because we're trying to learn a model for the environment on the fly so that we can improve our decisions. So data-driven decision-making, this is something that's really kind of becoming a central component in AI systems, and it's a very broad problem. There's many different ways we can model it and kind of attack it depending on the domain. So contextual bandits is this formulation that's widely used in recommendation systems, and reinforcement learning, of course, is this much more general formulation that we see applied to tasks like robotic control. And then we have these kind of more specialized formulations that we see in domains like medicine or operations research. So we have all these problems, and the way I like to think about this and kind of what will motivate the approach in this talk is thinking about this as a hierarchy of problems. The most basic problem is kind of supervised statistical learning or estimation, where everything is passive. And then going up a step, we have these problems like bandits or contextual bandits, where the decisions we take influence the feedback we see. So these kind of add an element of active data collection to the problem, and everything is online now. We have to make decisions on the fly. And then going up another step, bandits, this is usually referring to problems where we only care about immediate consequences of our decisions. But for RL and control, we go even further and we allow our decisions to influence how a stateful system is evolving. So we require long-term planning. But what I claim is within this picture, there's really a chasm between supervised learning and these interactive decision-making problems, both in terms of our capabilities and our understanding. And when I say gaps, what I'm really interested in here is understanding things like function approximation. What are the relevant measures of complexity for your problem that determine how many samples or trajectories you need to solve it? And what are the fundamental algorithmic principles? And so the idea we're going to explore in this talk is, given that we have all these different domains and different formulations of the interactive decision-making problem, can we get something like a unified approach to designing algorithms and to understanding sample complexity and statistical considerations so that we can, let's say, bridge this gap, and hopefully when we encounter new problems, mostly focus on modeling rather than algorithm design. And so the roadmap is going to be, we're going to sort of start by setting up the basic interactive decision problem and highlighting some challenges. And then I'll kind of introduce our new approach to decision making, and we'll see how it leads to algorithms and sample complexity guarantees through a bunch of just illustrative examples. All right, so let me dive in. So in this talk, the way we're going to formalize the interactive decision-making problem is using a framework that we call decision-making with structured observations. And this is just it's kind of a convenient language that captures pretty much any model for interactive decision-making you might have thought about before. So the setup is we're going to play for capital T rounds, where at each round little t, we're going to select what we call a decision pi t. So this is in a class big pi, which is like our decision space. And then based on this decision, we're going to receive a reward, RT, and an auxiliary observation, OT. Okay, so if you've looked at, like, say, bandit problems, this should be familiar. And I'll try to show in a second that this also encompasses episodic reinforcement learning. But first, I just want to get through a few more details. So first of all, we're going to be looking at what we'll call a stochastic setting, where we have what we'll call an underlying model, M star. So a model here is just a function that maps a decision to a distribution over rewards and observations. And we're just assuming that at each time, the rewards and observations are generated from M star, evaluated at the decision pi t we pick. We don't know M star, but what we're going to assume is that it belongs to some class script M. We'll call this a model class. And this is something you can think of as like capturing our prior knowledge about the problem in the same sense as like picking a hypothesis class encodes our prior knowledge when we do something like supervised learning. And so that's the basic statistical setup. The last thing to mention is the way we'll measure performance is through regret. So just what is the difference between the cumulative reward of the optimal decision for M star and the cumulative reward of the decisions that we pick. So just note here, I'm using F superscript M to denote the expected reward for a given decision when M is the underlying model. So like FM star here is just the expected reward for M star. Pi star is just the optimal decision for M star. Okay, and so to make this a little more concrete, we can look at a couple examples. Are there any questions about that basic setup, actually? Okay. Yeah. Oh.
Yeah, I had one brief question,
Sure.
which is I'm just curious. So this setup one can compare to a more general setup where the rewards are never observed, but need to be inferred from observation.
Sure.
So I'm just curious.
So, everything I'll say in this talk, all the upper bounds I'll give in this talk will apply to that setting. The lower bounds will not, and that's actually an interesting issue. So we can talk about that more later.
But how would that what should I be thinking about in this notation, like relative to that setting? Because I'm kind of
That's a different setting. I mean, yeah, that's more general.
Okay, thank you.
Maybe can I add just a little
Sure.
comment? The little comment would be that if the reward is a known function of the model, and basically the action taken or this pi, the policy or whatever, the decision taken, that's how you infer it, right? Like through the model.
For sure.
Alex, did it help?
Yeah. That's exactly what I was thinking about. Thank you.
Okay, so moving on to some examples, right? So, the simplest setting we can look at to kind of illustrate this is just the multi-armed bandit problem, which, should be pretty familiar for this audience. So this is just a setting where at each time I pick a discrete decision or action as we usually call it in this setting, I see a reward based on this action and nothing else. So like in the context of this general framework, there's no observations. Our decisions are this finite set 1 through big A. Our model class is just going to be like all possible reward distributions over these actions. So if we look at this class, which we'll call script FM here, which is just the mean rewards induced by our class, this is just going to be like R to the A, so all possible reward functions. The multi-armed bandit problem, this is like an unstructured setting where we have a finite set of actions. But by changing this model class, we can also handle settings where we have a large number of potentially structured decisions. So like if we look at linear bandits, this is the setting where now our decisions are like a possibly infinite subset of R to the D, but we're assuming the reward functions are linear, so we can generalize across actions or decisions. And another more general setting along these lines is non-parametric bandits. So here, same setup, but now I'm taking the mean reward functions to be Lipschitz rather than linear. And the way you capture both these models in our framework is just by taking script M to be the set of all models that have, say linear rewards or Lipschitz rewards. Naturally, there's other types of structure you can consider. Okay, moving on though. So far we haven't talked about observations at all, but sort of the most canonical example where these are important is reinforcement learning. And to show how this fits into the framework, we'll look at an episodic finite horizon RL setting. So here, our model class is going to consist of models that are like Markov decision processes with horizon H. So we have a state space, an action space, and then each model M is going to have a probability transition function PM associated with it and a reward distribution RM associated with it. And also, just an initial state distribution. And then the way a given episode in this Markov decision process will work is we're playing for H steps where we first sample the initial state from this initial state distribution. And then at each step, we select an action based on some policy that maps the current state to this action. And then we receive a reward based on the current state in action, and then transition to a new state based on, again, the current state in action. So in the context of this DMSO framework, our decision is just what policy do we execute for an episode, where this policy is just this mapping from states to actions. Our observations are the trajectory we see by executing the policy. So this sequence of states and actions and rewards. And then the reward function we're trying to maximize is the cumulative reward for the episode. So that's the basic setup. And this is a very general problem, right? So by choosing your model class script M, you can restrict what the rewards and transition probabilities look like. And there's a lot of flexibility in how you do this. Like you can say I have linear dynamics, you can assume I have low rank dynamics, and that's kind of just the beginning. Okay, so to summarize, we see that this DMSO framework, this captures a lot of well-studied models for decision making. And in general, what model works best for a given application, this is going to be like domain specific. And so the point is, we don't want to have to start from scratch every time we're faced with a new application. And so what we'd like to understand is whether we can have something like a unifying notion of problem complexity that captures the optimal statistical complexity for any setting. And when I say statistical complexity, what I really mean here is like, how is the optimal regret determined by the time horizon T you're looking at and this model class script M. All right, so the hope is, if we had such a complexity measure, this could guide us in designing algorithms so that we aren't starting from scratch in new domains. Okay, so to kind of try to motivate our results, I want to give a sense for why capturing the statistical complexity of decision making is challenging. And I want to try to convince you that this is a combination of both like algorithmic and statistical challenges. And these are intertwined in some sense. So to start, on the algorithmic side, the most basic challenge I want to highlight is exploration. And we can kind of exemplify this by coming back to the multi-armed bandit, right? So the issue in the multi-armed bandit is partial feedback. If we pick a given action, like what control signal to send to our robot, we only see how the system changes in response to this one input, and we only see feedback for this one input, but we don't know what would have happened if we had chosen a different action or input. And so this leads to this well-worn trade-off between exploring new actions, I should say, and exploiting what we already know. And of course, for the basic multi-armed bandit, this problem of how to balance exploration and exploitation is pretty well understood. But this setup on its own, doesn't capture stateful problems that require, like, say, long-term planning. Like if I think of a robot navigation task where I'm trying to make my way through a maze using vision, I'm going to have many different states now, and each state is going to have its own reward profile and a bandit type problem associated with it. So to generalize the picture I was showing for bandits, we can take the mean reward for each action and we can look at how this is varying as we go from like state to state. So here I'm using, these are like supposed to be images from my robot's camera to represent the state. And this is going to give me a full reward landscape where we've got, these potentially very high dimensional states as one axis, and we have actions as the other axis. And so now that we have this landscape, the key issue is, well, how do we simultaneously solve exploration but also generalization, right? So first of all, we still have to explore because we're only getting bandit feedback. Like we're only seeing what happens for the particular actions that we pick, which corresponds to, just like a particular point on this landscape. But at the same time, we have to worry about generalization because, again, these states can be very complex and high dimensional. Like if we have images from a camera, we don't have enough samples to get away with like say trying to treat each state as its own bandit problem. And so instead we need to somehow kind of propagate information across states or like across this landscape so that we can generalize and kind of intelligently explore or exploit even for states we've never seen before. But the issue is, in general, it's really not clear how to propagate information globally across a landscape like this. And this is especially true if you have an expressive class of models or functions. This is a problem, in some sense, it's very intimately tied to the problem of understanding how this model class you're working with determines the statistical complexity of the problem. And what I'll try to highlight is that like generalizing across states, and more broadly generalizing across actions or just across decisions, this is a really subtle issue, and it requires notions of problem complexity that go beyond classical notions like, say, VC dimension or Rademacher complexity. And the way I'll try to highlight this is just by going through some simple examples of different models and kind of looking at what makes them easy versus hard. Okay, so to start off with, for our first example, here's a bandit type problem where I have no observations, and so my goal is just to maximize a reward function. I've got 3 models in my class, and this graph is just plotting the mean reward function for each model. And so this is what I'll call an easy or even trivial problem. So we have multiple models with different reward functions, but they actually all agree on the optimal decision, like they have the same peak. And so this is easy because it means I can just commit to playing this decision up front. I don't need to explore at all to bother like figuring out what the underlying model is. So no exploration is required. But now we can change the model class slightly. And so if we look again, we still have 3 models, but now they all have distinct optima or distinct peaks. And so this means in order to optimize the reward, we need to actually explore the decision space now and try to figure out where the peak of the reward function is. And so this is kind of a harder problem. And in general, unless we assume further structure, the number of samples or like queries we need to solve this problem is going to scale with the number of optima. Okay, now I'll change the model class one more time. Okay, and if you look again, you'll see we still have different optima, like in this last example. But now if we look over on the right, we can see there's a single decision on this x-axis, which is not optimal for any of the models, but all of the 3 candidate models take very different function values here. And so the trick is we can solve this problem by just querying at this one informative point and estimating the function value here. And this is going to tell us what the underlying model is. And so we can deduce from this what the reward function is and what the optimal decision is. And so like by tweaking the function value slightly, we've ended up with another easy problem where we don't need to explore. So to summarize, if we want to characterize the statistical complexity of decision making, we kind of need to be able to distinguish between many different types of problem structure. So like, do we have many optimal decisions or few optimal decisions? Do decisions give us information about the whole landscape or just at a single point? And this is actually just the beginning. So like for all these examples I just covered, we were only looking at the mean reward function. But like in general, the distribution of the rewards itself can also like leak information about what the problem instance is. Like imagine a problem where I always have discrete noise for the optimal decision and Gaussian noise for the suboptimal decisions. Like this is something I can use to identify the optimal decision faster, and kind of any notion of complexity has to be able to account for this. And of course, all these issues are amplified when we look at problems like RL, where both the decisions and the observations are high dimensional, but also very structured. And so given that we have all these different factors that kind of affect the problem complexity in subtle ways, it's pretty natural to ask, I think, is it even possible to have like a complexity measure that can capture the sample complexity of decision making for all these different settings? But what I'm going to show you is, yeah, the answer is yes, with some caveats. So we have a new complexity measure called the decision estimation coefficient, which is both necessary and sufficient for low regret. And beyond just giving a notion of statistical complexity, it will actually give kind of like a new somewhat unified approach to designing algorithms. And so for the remainder of the talk, I'm going to try to introduce this complexity measure, and then we'll just go over a bunch of examples in Bandits and RL and try to give a sense for how this complexity measure behaves and how it sort of adapts to different problems. Okay, so let's dive in. So I'm displaying this complexity measure here, this decision estimation coefficient. And this is something that has 3 parameters. Okay, so this will depend on the model class script M. It's going to depend on what we'll call a reference model, M bar, in this class. And then it will depend on a scale parameter that we call gamma. And I'm displaying the full expression here, but there's kind of a lot going on, so we'll just walk through it step by step and kind of explain the interpretation. So the way we think about this is, this DEC, this is the value of a min-max game where the learner, which we represent by the min player, is trying to find a distribution over decisions such that if we look at a worst case model selected by the max player in our class, we want the suboptimality of our decision, which I'm highlighting here, under M. We want this to be controlled by sort of a notion of information gain relative to this reference model, M bar. Okay, so here we're quantifying information gain with Hellinger distance, which is this like information theoretic divergence. And we're looking at the distance between the distributions over rewards and observations induced by the decision that we select. So if we want this information gain to be large, you should be picking a decision where the corresponding distributions for M and M bar are very different. Okay, so to kind of say this again at a high level, the way to think about this is M bar is kind of something like a guess for what is the true model in my problem. And the DEC is asking, like in a very literal sense, what's the strategy for the learner that achieves the best trade-off between the instantaneous regret of their decision and the information that they acquire in the face of an unknown environment. And so this parameter gamma, this is just controlling the trade-off. Like it's controlling how much regret am I willing to incur to gather information. Okay, and I'll just mention, what we really care about here is the max of the DEC over all models M bar. So this is what I'm highlighting here in this box. And just one other note, I'll just mention, you can think of KL divergence here rather than Hellinger distance, if this is more familiar to you. So these you can relate under some like pretty mild conditions, which I'm highlighting here. And the difference will not be super important for the results I present unless you care about like log factors or other kind of problem dependent constants. Okay.
So Dylan, can I have a quick question about this information gain term there? So just to clarify that M of phi and this M bar of phi, these are just joint distributions over rewards and observations.
Yes, that's correct.
So they are not like posterior distributions or anything. So they are not really information gain in that sense.
Yeah.
Right?
So you can kind of like massage this thing around in different settings and get, say like priors and posteriors to appear here. Like if I do this for like the convex hull of a class of models. But yeah, in general, I kind of think about this as information gain. I'll actually sort of, I'll say a little bit more about the interpretation when we look at upper bounds based on this also.
Okay, because it just you mentioned this information ratio thing at the bottom, and that actually has like a pretty different notion of information gain.
That's correct.
Like posterior distributions.
Yes. I'll mention this a little bit more in a few slides also.
All right. Okay. Cool. Thanks.
Yeah. Okay. So this is like the basic definition of the DEC. And yeah. So the reason why we kind of care about this is something that gives necessary and sufficient conditions for sample efficient learning. So on the lower bound side, for starters, we can show that for any model class, the sort of mini-max regret for this model class, so the optimal regret for any algorithm, is lower bounded by the DEC for an appropriate value of this scale parameter gamma. And I'll go into more detail about this in a second, but the short version is that this lower bound based on the DEC, you can use this to recover the optimal rates for like all these different structured, bandit, and reinforcement learning problems throughout the literature, up to small polyfactors and some other like technical caveats. But what's especially exciting here is we don't just recover lower bounds for problems that are known to be tractable. We also recover kind of strong impossibility results. So like say like exponential lower bounds for certain problems. Now going to upper bounds, so there's a simple algorithmic principle associated with the DEC, which we call estimation to decisions, or E2D. And like conceptually, you can think of this as kind of a way of bridging decision making and estimation. So something that kind of reduces these decision making problems to supervised learning or estimation. And I'll just walk through the algorithm here. So the way this is going to work is at each round little t, we're going to use some kind of like supervised estimation algorithm, like think least squares or MLE, to estimate the model based on the data we've gathered so far. Okay, so once we have this estimate, which we'll call m hat t, we're going to find the distribution over decisions that solves the min-max problem corresponding to the DEC when m hat t is plugged in as the reference model. And I should mention, you should think of this Hellinger term, the DEC, as corresponding to kind of estimation error rather than information gain in this context. So it's kind of looking at how good an estimate is m hat t. But that's what we're going to do, is we're going to solve this min-max problem. And once we get this distribution PT out of it, we're just going to sample the decision for our current round from this distribution and play it. And then we'll update our estimation algorithm with the reward and the observation we get by doing this. Okay, so what you can show is if you run this meta algorithm, this estimation to decisions, your regret for decision making will be controlled by your error for estimation in a way that depends on the DEC. And to state this result in a little more detail, the way we'll define estimation error is just as the sum of Hellinger distances between the estimates we get from our supervised learning algorithm and the true model M star, but sort of for the decisions we're picking. So this is just measuring, how close is m hat t to the true model. And so what we have is that for any value of this scale parameter gamma, any value that you pick, I should say, so this is a parameter, the regret for E2D, this is going to be controlled by the DEC at scale gamma times t plus gamma times the supervised estimation error. So, conceptually, again, this is saying if the DEC is small and you can achieve good estimation error, you can get low regret. And the point I want to emphasize here is this estimation error, this is sort of like a classical quantity in online learning, which is just reflecting the statistical capacity of this class. So, you can show the scales as log cardinality of the model class for finite classes and scales with like the, feature dimension for like linear or parametric classes. But to give a little more intuition, it'll help to contrast this with a lower bound. And so we can show the following lower bound on regret in terms of the DEC, which hopefully will kind of look familiar coming from the last slide. So for any model class script M, what we have is that like the regret for any algorithm has to scale as the min of two quantities. So one is a kind of localized version of the DEC at scale gamma times t, and the other is gamma itself. And then we're just taking the worst case value of gamma here. So intuitively, this is saying if the DEC is large, your regret has to be large. But on the other hand, if we use a slightly more refined version of this estimation to decision algorithm, we can get an upper bound on regret that matches this, except that the gamma term in this min is going to be scaled by your estimation error. So overall, this is saying that, up to dependence on estimation error, the optimal regret is kind of determined by this DEC in a quantitative sense. And just to give a concrete example, if we look at the multi-armed bandit with A actions, I'll show in just a minute that the DEC at scale gamma grows as A over gamma here. And so if you plug this into your lower bound, you have the min of AT over gamma and gamma. the optimal value of gamma just balances these two terms. It gives you root AT, which is like the usual, minimax rate for this setting. And I'll go over more examples in a moment, but more broadly, the point here is like, because the form of the upper and lower bounds matches, we can extract from this a characterization for when learning is possible at all. So what we have is that, like, for any class where the statistical estimation capacity is bounded, you can have sublinear regret if and only if the DEC has polynomial decay as a function of gamma. And this is why we say it's necessary and sufficient. Zooming out a little bit though, like conceptually, I find this result exciting because it kind of gives a way of separating learning and estimation from decision making, and kind of bridging this gap in a way that I alluded to earlier. So the point is, like, for a given decision making problem, we can plug in our favorite algorithm for estimation, and this E2D kind of takes care of the rest. And so this means if we encounter new estimation or new decision making problems, we can focus on modeling and estimation and not so much on algorithm design. Okay, I'm just about done with the high level results, so I'll just give some quick kind of comments. So first, I'll just give a quick disclaimer and say, I've really only presented informal statements so far, and there are like kind of gaps in places where these upper bounds and lower bounds can be improved depending on what assumptions you make. So there are issues like, what is the precise localization radius you get? Like, is your class of models convex or not? Do you want in expectation statements or like in probability statements? And I won't have enough time in this talk to like go into as much detail about these issues as I would like to, but I'm happy to spend any amount of time like answering questions about these afterwards, because there are, I think, a lot of really interesting research directions here. I'll also just briefly discuss some connections to other notions of problem complexity you might have seen. So one, of course, is this information ratio of Russo and Van Roy. So this is another notion of complexity that was introduced originally in the Bayesian setting that kind of tries to look at the trade-off between regret and information, in a similar fashion. And you can show that the original version of the information ratio, like the original definition of Russo and Van Roy, so this always upper bounds the DEC, but in general, it can be kind of arbitrarily large in comparison. There is, however, a more recent generalization of the information ratio from Lattimore and Jörg. And this one you actually can relate to the DEC with some massaging if you have a convex model class. So this is kind of to Gergely's point before, you can play around with these like priors and posteriors. And yeah, I think it's interesting to explore this further. I don't think we fully understand this. And I'm happy to say more about that offline.
Dylan, very quick clarification question. Yeah. This complexity came up a bunch of times, but we haven't embedded the models into any vector space yet. So there you're kind of assuming something about the models that they live in.
Well, no, I mean, the models are like conditional distributions, right? So these naturally live in a vector space, right?
Okay, so that's what you mean. All right.
Yeah,
okay.
yeah.
Okay.
Cool.
Thanks.
Okay. So the other complexity measure I'll mention briefly is this this kind of Graves and Lie complexity measure. So this is something that has seen a lot of exploration in the context of structured bandits, and it's something that characterizes the optimal asymptotic instance-dependent regret rather than minimax regret in this setting. And this is a complexity measure where I would say we don't fully understand the connections to it. Like, it's not clear to me if this is useful for minimax rates in general, and kind of vice versa also. Like, it's not clear that the DEC is useful for instance-dependent rates in general. And yeah, I'm happy to discuss both of these more. Okay, so that kind of brings me to the end of the high-level results. What I want to do in the remainder of the talk is try to give a sense for how this DEC actually behaves and what these upper and lower bounds actually look like.
Can I stop you just for a second? I think James Michael Lee, he had a question and he's he just typed in. All right. Okay.
Well, yeah. So I mean, you're explaining that the E2D algorithm more or less reduces the decision-making problem to the estimation problem once you have the DEC. But the estimation term depends on what the algorithm, the choices it's making. So they're not decoupled. While I do understand that
Oh
you
yeah.
can find, like, you can certainly find an estimation algorithm that will achieve the lower bound. Those are special in the sense that they're like mixtures of experts. But like if I take a generic algest, it's not clear that it wouldn't behave badly with the decisions that E2D is making.
Yeah, so that's true.
You see
so,
what,
yeah, so the precise guarantee you need, right, is you need an algorithm for like online estimation. So like an algorithm for online learning with the model class. Like whenever you have an algorithm whenever you have an algorithm for online learning that actually has like a regret bound for individual sequence prediction, you can ensure that this complexity is bounded. But reducing it to like sort of like passive estimation, like offline estimation, this is a very good question.
but even online, like your decision,
yeah.
like
so
you're taking decisions according to the
estimation.
algorithm.
Yes, the point of online estimation is it ensures that this is bounded even though these decisions are made in an active fashion. You can check out the paper for details.
Okay.
Okay, so yeah, so to kind of give a sense for how this behaves, we're going to look at 5 examples, and these are going to highlight some sort of different features of problem complexity. So we're going to start by looking at some bandit-like examples that kind of capture how the DEC is able to adapt to the structure of the reward distribution. And then we'll look at an example that's more information theoretic in nature. And finally, we'll kind of look at tabular reinforcement learning, where we have observations in the picture again. And those will be the main examples, but I'll try to say a little bit about like more rich RL settings if there's time as well. Okay, so let's start. So the first example, we're going to come back to the multi-armed bandit. And just to recap again, our decisions here are just this discrete set 1 through A. We have no observations. And our model class is just the set of all reward distributions. So I'm displaying the DEC here in the original form. But if we want to make this a little more interpretable, for this bandit setting, we can actually simplify it a little bit and replace Hellinger distance with squared distance between the means. And the intuition here is just because I'm placing no assumption on the reward distributions I'm considering, other than that they're like, say, 1 sub Gaussian, the max player can just add white noise. And this makes it so that only the mean rewards are informative. So like the mean rewards act as a sufficient statistic. And I'm just displaying this modified version of the DEC here. We're calling this DEC superscript SQ for squared. And this is equal to the original version up to constant factors for this setting, but it's a little simpler to manipulate. Okay, and so as I claimed before, we have these upper and lower bounds on the DEC that show that it scales as A over gamma for this setting, and this gives this root AT lower bound. But what I'll try to do now is show how we actually derive, the complexity of the DEC for this setting. So how do we calculate the DEC? So on the upper bound side, there's 2 different approaches we can use to bound the DEC for bandits, and both of these will involve exhibiting a specific strategy that solves the minimax problem. The first is to use a technique called inverse gap weighting. And the way this works is that we're going to have this model M bar, which we can think of as an estimate for rewards in this setting. And we're also going to have this parameter gamma. And with this inverse gap weighting is going to assign a probability to each action that's inversely proportional to the gap between the reward for this action, the estimated reward, and the estimated reward of the actual, well, the highest estimated reward, like the max estimated reward. So that's why we call this inverse gap weighting. It's inversely proportional to the gap. And then we scale the gap by this parameter gamma and add a constant, like a normalization constant lambda, which is chosen so that these sum to 1. And so what you can show is that this is actually like the exact minimizer for the bandit setting. And this leads to, so it exactly solves the minimax problem. And this leads to this A over gamma bound. And I'll show in a sec why this actually leads to this A over gamma bound. But first I want to sketch another approach, which is to appeal to Bayesian methods. And the idea here is like, okay, why are we appealing to Bayesian methods? Like I've only been talking about the frequentist setting up until this point. But so what we can do is, so like we can look at the original DEC, which is where we're picking a distribution over decisions, and then the adversary is picking the max over models. But then we can convexify this max by considering a max over distributions, and then apply the minimax theorem so that we end up with a game where the adversary is first picking up prior over models, and then we're picking our decision distribution with knowledge of this prior. And so once we have this Bayesian game, we can just appeal to like, posterior sampling or probability matching, like just pick the distribution over decisions induced by sampling from the prior and playing the optimal decision. So this also leads to this A over gamma bound. Okay, and I'm going to sketch the proof for the inverse gap weighting now, but the reason why I wanted to show both approaches is that they actually both extend like far beyond the basic bandit setting. Okay, let me just sketch this proof for how the inverse gap weighting leads to a bound on the DEC. So I'm displaying the scheme here again, this inverse gap weighting scheme, and bounding the DEC means proving that if we select our actions with this scheme, then for any model, our expected regret should be bounded by A over gamma plus gamma times this squared error between the means, right? So this is kind of, you can think of as estimation error. Okay, so the way we'll prove this is we're going to fix a model M, and we're going to split this regret or suboptimality on the left into 3 terms. One is what we'll call like exploration bias. One is what we'll call on policy estimation error. And one is what we'll call estimation error at the optimum. And we'll bound these terms one by one using different properties. Okay, so let's first look at exploration bias. This is term 1. This is asking, suppose my model M bar was correct, then how much am I paying for exploration? Okay, so what we can do here is, I've just expanded this definition of the exploration bias using the definition for P. What we have here is just sum over all actions, regret of the action divided by lambda plus gamma, times regret, times the same quantity. So we can drop this lambda term in the denominator because it's non-negative. And then this regret in the numerator and the denominator, this cancels, and we're just left with A over gamma. So this says, if my estimate's correct, we're only losing an A over gamma factor in exploration. Okay, now if we come to the second term, this I'm calling on policy estimation error. This is just the difference between the mean reward for M bar and for M under our own distribution P. And because it's under our own distribution, like this is why I'm calling it on policy, it's very easy to relate this to squared error. So we just use Cauchy-Schwarz to bound this by the root mean squared error. And then we use AMGM to bound this by 1 over gamma plus gamma times squared estimation error. And that's it. And I should say, this bound actually is not using any properties of the inverse gap weighting. And this constant gamma I'm picking here is arbitrary. Like I'm just picking this to match the bound we already picked up from the first term. Okay, I'll move on to the final term now. So this is what I'm calling estimation error at the optimum. This is saying, how much do M and M bar disagree on what the optimal value is? And this is a trickier term because it's looking at on policy. It's not looking at on policy error. It's just looking at error for these fixed actions. But somehow I want to bound it by estimation error under my own distribution. And so to do this, we'll use the structure of the inverse gap weighting distribution and try to argue that like either we put a lot of mass on pi star M or our estimation error has to be big. Okay, and so the way we'll do this is we're going to split this as just the difference in the mean rewards at pi star M minus the suboptimality of pi star M, so that's what I'm highlighting in orange, minus the suboptimality of pi star M under M bar, which is in blue. We're going to do AMGM on this first term again to split it into something like squared error plus a 1 over gamma term. But now I'm using AMGM to introduce the probability mass on pi star M. Okay, and then we can just upper bound this first term by estimation error. So what we're really left with here is the second term, which has this 1 over probability of pi star M. And this is really asking, like, did we put enough mass on the optimal action? Okay, so what we can do here is we can expand the definition of P from this inverse gap weighting distribution. And what we'll get is lambda plus gamma times the regret divided by gamma. And so what happens is these gamma terms cancel, and this regret is actually canceled by this negative offset. So I'm left with just lambda over gamma. And you can show that lambda is never bigger than A. So I get just A over gamma, and that's it. Like that's how you bound the DEC for multi-armed bandits. Okay, and I won't go into more detail in this talk, but you can check out the paper if you want to see a corresponding lower bound on the DEC, which is somehow much easier to prove. Okay, are there any questions about this calculation? All right. Okay, so let's move on to another example. That's the only one I'll go into in like super detail. So the next example is going to be full information. And the setup here is exactly the same as the bandit. So my decision space still consists of A actions, but now I'm going to make it so that the observations actually have the reward for every possible action. So in other words, like I'm still picking an action and incurring the reward for this action at each round, but now I get to see what I would have achieved if I'd played all the other actions. And this is a setting that lies at the opposite end of the spectrum from bandits in terms of how much a decision reveals information about the other actions. So in bandits, a given action might tell you nothing about the rewards of the other actions, whereas here it tells you about the rewards of all the actions. And indeed, what you can show for the setting is the DEC scales as 1 over gamma rather than A over gamma. So you get root AT rather than, or sorry, you get root T rather than root AT as your regret. And the intuition is just, you can pick the decision P or the distribution P in the DEC to just play the greedy action for the estimated model M bar because the information gain in the DEC is going to be equally large regardless of what decision we play. So like exploration is not required at all. Okay, now moving on. So bandits and full information are at opposite ends of the spectrum in terms of how much information different decisions reveal about the rewards of other decisions. If we come back to structured bandits, this is kind of in the middle of the spectrum. So for example, for linear bandits, we have our decisions, you know, again, are some subset of R to the D, and our class script M is just all the models with linear mean reward functions. And so here you can show the DEC scales as D over gamma, where D is like the action dimension. So this gives like a root DT bound. And the point is like, so this looks a lot like the bound for the bandit setting, except the number of actions is replaced by the dimension. And the point is, you know, because my decision space is structured, like once I have kind of see D fully independent directions, I can estimate the rewards pretty well. So like it suffices to, you know, explore on a well-chosen basis. And that's indeed is kind of how you prove upper and lower bounds on the DEC for this setting. You kind of combine this inverse gap weighting with the idea of exploring on a representative basis. Okay, now one point I'll briefly mention here is, so this behavior we've seen in all these examples so far kind of looks something like effective dimension over gamma. And this is very common. Like you also see this scaling with like, say like convex bandits and generalized linear bandits. But in general, we have different scaling for like harder problems where the optimal rates are worse than root T. So for example, if we come back to non-parametric bandits where our models just have Lipschitz mean reward functions, we get a different polynomial behavior, which reflects the fact that this is a non-parametric setting. So like the DEC here scales as roughly 1 over gamma to the 1 over D. And so you get a regret lower bound of T to the D plus 1 over D plus 2. So this is getting worse as D gets big. Okay, I'll move on to another example. So for all the examples so far, somehow the mean rewards were the only important feature. But we're going to look now at a bandit problem where the sort of optimal thing to do is kind of more information theoretic in nature. So we're going to look at, again, a bandit type problem where our decision space has A actions. But now, for all the models in our class, the reward is Bernoulli with like a slight positive bias if you take the optimal action, but it's Gaussian if you take any of the other actions. So now it's bandit still, but like the distribution of the rewards depends on the arm in a structured way. And so the point is for this setting, the DEC has kind of like a stepwise behavior where it goes to 0 once gamma is bigger than the number of actions, and it's constant otherwise. And so if you plug this into our main theorem, you get a regret lower bound that's just linear in A and independent of the time horizon. So much faster than root AT for like regular bandits. And so conceptually, this is saying, okay, because you're using an information theoretic divergence like Hellinger, although, you know, KL would also be fine, you know, you can immediately detect the difference between Gaussian and Bernoulli from a single arm pull, which means you just need to try every arm once until you identify the right one. And so that's why DEC with Hellinger works. But if you were to look at DEC with squared error, which only like looks at the difference in mean rewards and not the difference in distribution, this can't distinguish between this problem and like vanilla bandits. So it doesn't have the right behavior. And just a like kind of a conceptual note here is like, you can generalize this idea of problems where the noise is informative very far. So like you can think of bandit problems where all the rewards look Gaussian, but when I go like 100 bits down into the binary representation of the rewards, I've embedded some string that encodes like arbitrary auxiliary information. So in some sense, if you're trying to solve bandit problems with arbitrary structured noise, you should be able to solve bandits with auxiliary observations. And the point of this framework we've been using in this talk is just to make that fact explicitly, because it's somehow very useful to be able to handle observations. And so with that in mind, I'll just go to this last example, which is the canonical setting with observations. So just reinforcement learning. And coming back to reinforcement learning, so, you know, our model class here is just going to be the set of horizon H MDPs with finite states and actions. So S is the number of states, A is the number of actions. And our decision space is just, you know, again, policies that map states to actions. And observations, these are just trajectories. So on the lower bound side here, you can show that the DEC grows as HSA over gamma. So this gives a like root HSAT, lower bound on regret. And on the upper bound side, you can get guarantees that you know, match this except for dependence on the time horizon. So you can do this using a generalization of this inverse gap weighting technique we showed for bandits. And you can also do this using this posterior sampling idea. So like going to the Bayesian setting. And I will say improving the dependence on H here is like a pretty interesting question. But both of these are kind of taking advantage of the fact that you have trajectories. Like if you just see rewards here, you know, you do have to pay for exponential sample complexity and horizon. Okay, I'm very close to the end of the talk. I'll just briefly say a little bit more about how do we derive this upper bound for tabular RL, because it combines, it kind of extends this inverse gap weighting technique for bandits and gives like a new algorithm. And the basic idea is we use the same scheme where we're assigning a probability to each decision that's inversely proportional to its like estimated reward gap. But here our decisions are policies rather than actions. And like naively, there's exponentially many policies. So we can't just naively apply inverse gap weighting to all of them. This is going to explore too much. Like it doesn't take advantage of information sharing. And so instead, we're going to first come up with a representative set of policies that we call policy cover. And then we apply inverse gap weighting just to this subset. And so what I'm displaying here is just the first step of how we choose this subset. So the way this works is we have this estimated model M bar. And what we do is for each time horizon H, little h, for each state S and for each action A, we find the policy that maximizes the ratio of two terms. So the top is the probability that we visit state S and action A at time H. And the bottom is the estimated reward under M bar scaled by gamma. So this is saying you're balancing reaching a state and action with having small regret. And so what we're doing is we're computing a policy like this for each H, S, and A. And we're also computing the optimal policy for M bar. And we're taking this to be our policy cover, which we're calling psi. And then once we have this policy cover, we just do the regular inverse gap weighting scheme, but only to this subset of policies. And that's it. So you might be wondering, well, like, why does this work? And the basic answer is, like, this construction ensures that you have good coverage at every state, but at the same time, it ensures that you don't incur very large regret while trying to maintain this coverage. And so because you have good coverage, things go through like in the bandit case, even though you have a small subset of policies. The only issue is we're computing these policies to maximize coverage at the estimated model. And what we care about is coverage at the true model. But you can use kind of a change of measure type argument to show that, planning with M-bar either implies good coverage in the true model or your estimation error has to be big. And this can kind of only be big so many times. Okay, the very last thing I'll do is just give a short teaser for sort of what do the RL results look like when you go beyond tabular methods. The point here is like, for RL, beyond the tabular setting, we want to handle like large state spaces. So we need to use this model class to try to like generalize across states. And there's a couple ways you can formalize this, right? So one way to do this is to look at, what we kind of call model-based methods, where script M parameterizes the transition dynamics for your MDP. So like, script M could be saying this is a class of linear dynamical systems. And another way is to look at like value-based methods. And usually the way we set this up here is we have a restricted class of Q functions, like linear models or neural nets. And we're going to assume that, like, say, the optimal Q function for the MDP lies in this class, or maybe all Q functions for the MDP lie in this class, or it could be some other property like completeness. But the way you can view this in our setting is just to take your model class script M to be the set of all models that are consistent with this Q function class for whatever your favorite notion of consistency is. And when it comes to lower bounds, this viewpoint is sort of without loss of generality. Okay, so there are many examples of both of these approaches. There are also many sort of general structural conditions that try to subsume all these examples, so sort of giving structural conditions under which sample efficient RL is possible. So for example, we have this notion of Bellman rank, which is trying to control like the number of effective state distributions in your problem. We have this notion called a Luder dimension, which is trying to capture, to what extent does your value function class facilitate extrapolation? And there's many variants that like build on combine these approaches. And so I won't go into detail, but you can show that the DEC can be bounded in terms of all of these different complexity measures. So for example, for Bellman rank, you can show that the DEC at scale gamma is roughly bounded by, Bellman rank over gamma. And this is actually a kind of cool result. Like this actually combines this policy cover inverse gap weighting algorithm I was just showing with experimental design. Okay, and I'll briefly say I was talking about upper bounds here, but again, the real distinction is like the DEC is giving a necessary condition and it leads to lower bounds. So for example, we can recover these recent lower bounds that show that sample efficient learning with only linearly realizable Q star functions is intractable. Okay, I'm at the end now, so let me summarize. So we saw that this DEC, this gives a complexity measure for interactive decision making, like bandits, reinforcement learning, beyond, that's necessary and sufficient. And I find this exciting because it gives kind of like, I think a good like foundation on which to build like a unified theory through which to attack these different problems. And I'll just give a teaser and say like you can check out the paper for a lot of further applications, examples that I didn't have time to cover. And I'll just say for future directions, like on the algorithmic side, we've actually already seen that for contextual bandits, the algorithms that come out of this approach are super practical and actually even have state-of-the-art performance. And I'm just giving a teaser on the right, but like, if you want to check out the VW library for machine learning, you can actually just already pull the contextual bandit algorithms that come out of this framework and just run them. It works really well. But I think what's really interesting is like, can we get further practical insights here when you go beyond like Horizon 1? So for RL, like, and I also think it's interesting to think about like, how can we take the techniques from this framework beyond just the setting of this talk? So for example, like how to handle observational data. And yeah, the last thing I'll just say is, really this is just the beginning. And especially on the technical side, there are many very interesting questions, and I'm happy to chat about all of these more offline. But I think I'll end it there.
All right, great. Thank you, Dylan. Wonderful.
Cool.
Very nice. Yeah. So for those of you that did not read the paper, this is over 100 pages compressed into 1 hour. So So there's plenty of stuff to talk about.
I don't want
Here.
the like page length to like scare anyone, because it's really just like, you know, main results, and then we just have many examples. But like you can easily dive into this and just get a sense for like, I think, the main results very quickly.
Yeah, that's right. That's my experience as well reading the paper. So there have been like a bunch of questions in the chat. I guess some of those are very technical.
Okay.
So maybe let me just ask, well,
Sure.
I don't know if that's a complicated question, but I'm just really wondering about the precise role of this Hallinger distance that you use in the definition, because it seems to me that in the upper bounds, at least the ones that you've shown, you're using the squared loss, and in the lower bounds, you're using the KL divergence.
Right.
So is there like any concrete setting where the choice of Hallinger actually becomes important?
No. So for the upper bounds, I should say the only reason we're using we talked about square loss is specifically for these like bandit type problems. And for RL problems, you really do want to use like Hallinger or KL in general. Although, like, you know, for specific problems, there are kind of weaker notions of sufficient statistics that you might want to like try to estimate instead of KL or Hallinger. And trying to understand kind of like what the weakest notion of distance you can use in a systematic way is very interesting. But to get to the specific issue of Hallinger versus KL, it's not a big difference. This is just kind of the presenting things in terms of Hallinger, I think, makes the upper and lower bounds kind of cleanest in the simplest way possible. So another way of saying this is like for KL, you can get upper bounds in terms of DEC with like forward KL and lower bounds in terms of DEC with reverse KL. And then the question is like, when do these match? And so you can try to like, you know, smooth out your distributions and, you know, use like kind of density ratio arguments to relate these things. And doing it with Hallinger just makes it so that you don't have to do this. This is kind of built in. But Hallinger is also very useful on the upper bound side because so usually the way you measure, you actually, you know, get an estimation bound here is to use an algorithm that has low regret with log loss. And if you just care about in expectation regret upper bounds, you know, this is fine. Like minimizing log loss immediately leads to a bound on KL. But in general, if you want things in probability, minimizing log loss regret does not give a bound on KL unless you sort of make boundedness assumptions, whereas it always leads to a bound on Hallinger with no assumptions. But yeah, it's not super important as long as you're working with like, you know, say like bounded rewards.
Right, I see. And then regarding these RL algorithms that you have derived, like this, so this looks fairly complicated to me. Do you think that something easier could be derived from this decision estimating coefficient, or this E2D principle? Does it like still apply in your mind to this RL setting, or is this something different? I had a bit of a hard time understanding.
Oh yeah, I mean the algorithm I was giving, right? That was just a choice for the P that attains the argument. Well, it certifies an upper bound on the DEC, but I'm just saying it's just a choice for the P in the DEC. So this is still going through the general principle, right? But yeah, so I don't know. I mean, I find this algorithm, so it's different, but I mean it's I would describe it as like fairly simple in the sense that it's really just find a representative subset, do inverse gap weighting on top. So if you do it that way, it's really not a super complicated algorithm. It is an interesting question of, can you do something a little more like step by step, like rather than global, like something that kind of uses maybe like the inverse gap weighting in tandem with like dynamic programming? That's an interesting question, and I don't know the answer.
And the results that you have for Townsend sampling, are those for the Bayesian setup or
oh, right.
Frequentist, or
no, so well the posterior sampling, what I was highlighting there, so there's a couple ways you can view this, right? So like, first of all, whenever you have, so you can use these to certify an upper bound on this frequentist DEC, but it doesn't give a constructive algorithm for the frequentist DEC, right?
Oh, I see. So it's not a bound that holds for Townsend sampling, but rather a bound that certifies that indeed this bound is achievable.
So this is just kind of a mathematical approach to figure out that the DEC is bounded. Now, that said, if you are in the Bayesian setting, there's kind of like a Bayesian analog of this like E2D that you can use. And for this one, like the posterior sampling, is constructive. Like you can just use posterior. I mean, it's at this point, it's just posterior sampling at that point, or like modified posterior sampling.
Right. So in the chat, Ronald was asking if you have any results for non-episodic reinforcement learning.
Haven't looked into this at all. So this is a good question. Like, how do you extend the results here to kind of like single trajectory settings? Yeah, interesting question. But we've not really started to explore that at all.
There was earlier also a question by Pierre Kumar, or he actually phrased it as a comment. So back in the 1979 and around the 80s, there was a line of work that was trying to do something very similar to this. So I'm not sure whether you're familiar with that, and if you are, then how does it compare to what you're doing?
I don't think I'm familiar with this like off the top of my head. Unless is there like a specific reference or something? Like
so he's actually here. He can ask his question.
Okay.
I guess in more detail. I think
hear you.
He's muted.
Can you hear me?
Yes.
Yeah. Okay. So we were. I'm a little bit of a fossil here. So when we looked at this in 1978, 79, we were looking at MDPs, and it was called adaptive control, and the focus was on trying to prove long-term average optimality, and then subsequently Lai introduced regret, but this was before regret, and we were just trying to prove regret is little of t. And then there was a line of work where we did this for lots of nonlinear stochastic systems. And
so can you tell us something about the idea of these papers?
So very simple. So the idea is, let me tell this in the MDP context, okay? So for, you basically have two terms. One is the reward or the cost of a model, okay? And then the other is the likelihood ratio or likelihood. So that's like KL, okay? So it is reward plus cost or minus, depending on which, you want a good fit and you want a high reward. And there's a pre-constant, a function of time actually multiplying the reward. Okay, so you want to buy, we call it cost-biased maximum likelihood. You want to make a maximum likelihood estimate of the model, but you prefer models with lower costs. And the reason for that is it's not arbitrary. It turns out that if you just do, say, certainty, just estimate likelihood ratio, play the best action, then you converge to a model which is indistinguishable from the true model under the optimal policy corresponding to the estimated model. So you will not, it's an exploration dilemma. And it turns out that within that set, the rewards or the costs are always worse than the optimal cost. So and therefore you should, if you can bias it delicately towards a lower cost, then you can get the best of both worlds. And that extends to long-term average optimality. And recently we've been trying to show all this for regrets and so on. And in the single trajectory case that was just asked. So all the early results are only the single trajectory case. Now we are looking at also the episodic and so on.
I wonder, so here the spin was that this is very general. So did you try something similar and some characterization of learnability? Like, can we get sublinear regret? I guess you said that it was no regret at the time, but like, I don't know, like you had similar asymptotic convergence guarantees in like some university. Like, did you try to go towards this direction as well?
So I don't think we've done it in the immense generality that you have done. We looked originally at MDPs, and then it turns out that for bandit problem, you get simple index rules, explicit index rules, which actually perform very, very well. We've also done it for linear contextual bandits, and we've done it for LTG, okay, but not in super duper generality.
So maybe it's versatile in the future too. Yeah, come back to this.
Yeah, I mean, yeah. So I guess like I'm happy to check this out. It sounds interesting. Like, yeah, it's without. I guess I don't fully understand like the scope of this right now, but yeah, it sounds interesting.
I can chat with you offline.
Sure.
Cool.
That's very nice. So Sharon, you had a question that we can ask if you're here.
Sharon? No? Yeah?
He just asked his question and he left. Or... Okay, anyhow, he's asking... okay.
Oh, no, I'm here. Sorry.
Oh, okay.
So are there other ways to find this P in this min-max game other than this inverse gap weighting thing?
Good question. I mean, I think the short answer is we don't fully understand this yet. I mean, like, we certainly have ways of like deducing that the value of this thing is bounded without using the inverse gap weighting. Like this min-max approach I sort of mentioned is that gives a very general tool for doing this. But like in some sense, all of the constructive algorithms we found use some variant of this. Now, are there cases where you should go beyond this? There are definitely like specific cases, but for like these kind of general models, like, you know, things like MDPs and so forth, they all sort of use this basic idea. So this is definitely something that's interesting to try to explore further. Another thing we've been exploring is just figuring out when can we get generic kind of like iterative methods to try to find P's that minimize this thing without having to actually do math to, you know, or like to come up.
Okay, yeah, that's what I had in mind.
Yeah.
Okay.
So yeah, it's something we're exploring right now.
And the other question was, do you have instance-dependent bounds using this kind of framework? That would be cool.
No, not right now, at least. I mean, yeah. So instance-dependent bounds. I mean, there's various ways that you can define what you mean by an instance-dependent bound. So, like, if you care about like sort of asymptotic instance optimality, I don't think this is necessarily the right complexity measure. And there's this older notion of Graves and Lie, which kind of does give the right behavior asymptotically. But like, I wouldn't say we understand what the right story is for like finite samples. That's very interesting to explore.
I see. All right. Thank you.
So Alex has the recurring question he asked earlier, and he came back to it, and then it's a good question, I think. Do you want to ask?
Hi.
Yeah.
I can ask.
Sure.
So I'm very interested, actually, I have a number of questions about the specific properties of the zero-sum game that is used in defining DEC. And the first thing, which is that you said during the talk that inverse gap weighting is actually the optimal strategy of the game, which it could be that I like just missed it, but I didn't see anywhere in the paper. And I want to know
so if you want to see that, so there's a paper, an older paper we have, which is called Adapting to Misspecification in Contextual Bandits. It should be cited in this paper, but if you look at that paper, we have the calculation there.
Okay, and can you comment on like roughly what kind of technique is used for that? But I'll definitely look at that paper. Yeah,
just calculus, basically. I mean, like, okay. So the only trick,
it's a thing that goes from just directly like taking like a calculus of variation kind of calculation or something.
Yeah. So no. All it is okay. So the only real trick is, so you have a max over f's, and then you also have like the optimal value for the given f you're looking at. And so you swap the order of these. So you're doing like max over actions and then max over f's. And for any action, you can just, you know, compute the optimal f that attains the max using like first order conditions. Like it's really just checking the first.
No, that makes complete sense. Thank you. Yeah. And I have some more questions actually about like specific properties of that game because I'm very interested in that. I know there's other questions in the chat, so I'm going to come back to that later.
Yeah, but I guess maybe more on this. Maybe there's a bit of a misunderstanding here because so that optimal solution that is given by the inverse gap weighting, that is actually on a relaxed version of the original DEC, right?
You mean the square loss version?
Right. Where you replace the Hellinger distance with the squared loss.
That's right.
And for that, it is the optimal solution. For the Hellinger distance version, it's not necessarily the optimal one.
Yeah. That's right.
Right.
I didn't get what the relaxation was because the doggies are very excited about something.
No, we're just saying like it's the exact solution for the DEC with square loss, not necessarily the exact solution for the DEC with Hellinger or KL.
Yeah, that makes sense.
And so, for example, especially if you know something about the reward distribution or even the reward range, you can do better than this. So, for example, if you know the rewards lie in 0 and 1, then we have this variant that takes advantage of this to get sort of like small loss or like first order regret bounds. And that one you kind of can view as coming out of looking at like Hellinger rather than squared error. Yeah, that's from this like Nariv's paper last year, which is called Efficient First Order Contextual Bandits, if anyone wants to, in case you want to look that up. Yeah.
All right, so PR Kumar has a hand up.
I had a question about your criterion. When you play with Hellinger or KL or whatever, is one of them, I mean, KL is not going to give you a convex overall criterion, right?
Wait, what do you mean by criterion?
So your min-max problem, you cannot convert it into a convex problem.
The tech problem.
Yeah. So
yeah, sure.
Hellinger,
well, sorry. Actually, just a quick
convexity. Yeah, sorry.
It's always convex with respect to the learner's distribution P, because it's just a max over like an expectation under this distribution. So for the learner, it's just a max over linear functions, but it's not necessarily convex with respect to it's not necessarily concave with respect to the M player.
Mm-hmm.
It's actually, so it's almost concave with respect to the M player. The thing that messes up concavity for the M player is just the fact that you have the max reward for M.
Yes, exactly. Yeah. So I was just wondering whether Hellinger helps in that context, or maybe some other different.
It doesn't really matter. Like all of the standard like F divergences are going to be like they're convex, and so this makes it so that when you have minus Hellinger or minus KL, it's concave with respect to the M player, which is good. Like that's what you want actually. But just to be clear, when I talk about doing these like things like the mini-max swap, like in the talk, for that what we're doing is we're just convexifying this thing, right? We're going from pure models to distributions over models, right? So that like going to a distribution over models just makes it convex with respect to makes it concave with respect to the distribution.
But then you go to an infinite dimensional space.
Yeah.
Okay. All right. So you're convexifying by putting it in a higher dimensional space. Okay.
Yeah, it's just that it turns out to be a useful it's a useful tool here. It's not always a useful tool, but yeah.
So Kwang had a comment about, I guess, like other distributions that can achieve bounds in the DEC. I don't know, Kwang, can you elaborate if you're still here?
Oh yeah, I was just mentioning in response to Sharon's question, are there other ways to find P besides the inverse cap weighting? I guess I was saying not generically, but there's for K-arm bandits, there are other weighting scheme, which is like exponentiated minus gap squared with a modulo some other constant there.
Wait, Kwang, so I've actually not looked into this, but now that you mentioned it, I'm curious. Wait, can you actually show that the Multiarmed sampling that actually like certifies a bound on the DEC? Because like I know it works for bandits, but I never checked whether like say that you can view this as certifying a bound on the DEC, because that would be interesting.
Yeah, that would be interesting. I never considered that one, but yeah.
Okay.
Into it. Yeah,
that would be interesting, because like, you know, if that certifies the bound on the DEC, okay, like a cool feature, which I didn't talk about at all in the talk, but which is true, is like anytime you have a bound on the DEC for some class, you can immediately lift that to like the sort of contextual version of the same problem. So like if the Multiarmed sampling works for just regular DEC, I would assume that means you can also use it for like contextual bandits in the same fashion.
Yeah.
Square CB.
That'd be very interesting. Yeah.
Yeah. All right, cool.